Okay, we'd like to start final session of the symposium. Okay, welcome to the final session of the symposium. This is for SLAC, it's the D3 Session 3 channel. And there'll be 4 talks. Each is 10 minutes long, and I'll give the speakers a 2-minute warning. And the first talk is Searching for FRB-like Counterparts from GRBs Using the First CHIME FRB Catalog by Alice Curtin.
Okay, great. I'm Alice Curtin. I'm a PhD candidate at McGill University, working with Vicky and also with the CHIME FRB collaboration. And today I want to talk to you a little bit about some work I've been doing to look for coincident FRBs and GRBs. So we're at an FRB symposium and we're very kind of late into the session, so I probably don't need to go over this slide in detail, but just a reminder that in 2020 we detected an FRB-like burst from SGR 1935 plus 2154, and we detected it in both the radio and the soft gamma ray hard X-ray, but we have yet to unambiguously detect any extragalactic high energy emission. So this is where gamma ray bursts come in, and we're at an FRB symposium, so I'll give a little bit of background to gamma ray bursts for those that aren't super familiar. So we typically think of them in 2 categories. We've got these shorter gamma ray bursts coming from compact object mergers, although we've also seen kind of short gamma ray burst features from magnetar giant flares. And then we've got longer gamma ray bursts typically produced after the collapse of a massive rapidly rotating star, although there's also some research to suggest that they can similarly come from compact object mergers. And so this is where kind of my question comes in. Could FRBs and GRBs be related? And we've heard kind of quite a bit already today from Sriharsh and Kelly about some theories that suggest they could. And in particular, I'm interested in whether FRBs and GRBs created by compact object mergers could be related. And so pre-merger, if you have 2 neutron stars inspiraling, you can get precursor winds and interactions between the magnetic fields to produce these FRB-like bursts. Or you could have a neutron star black hole binary battery producing this FRB-like emission. And then after the merger, given kind of certain neutron star parameters, so spin, neutron star equation of state, you could produce this stable neutron star that might be able to kind of emit pulsar-like emission. And then if you have this unstable neutron star that collapses to form a black hole, then you could also get this one-off FRB-like burst then. So here's my work comes in. So for FRBs, we've got the first CHIME FRB catalog, so 536 FRBs over a roughly 1-year time frame. And then the GRB sample is all GRBs kind of reported in GCNs in the same time frame. But then I only use the bursts that are quote-unquote like well localized, where here I define that as less than a degree. Probably for many of you out there that isn't actually so well localized. And then they have to have available high energy fluxes and fluences. So this leaves us with 81 GRBs in roughly the same time frame. So the first thing that I search for is temporal and spatial coincidence. So I'm looking for FRB and GRB pairs that are coincident within 7 days of each other, and also having their 3 sigma localization uncertainty regions overlapping. And as the title of my talk probably gave away, we didn't find anything using these criteria, but we did find these 2 pairs that are solely spatially coincident, but the chance of this happening is pretty high. So we went about determining that chance in using 2 different methods. So first, we simulated a set of FRBs by making a 2D probability density distribution in both declination and time to create a simulated set of FRBs on the sphere. And then we cross-checked that with our 2 sample of GRBs. And then on the other side, we created this simulated set of GRBs randomly distributed on the sphere and cross-checked that with our FRB sample. And in both cases, we found that the chance probability of this happening was very high, and so we can't claim that we have any significant coincident FRB-GRB pairs. And all that I'm showing here on the right is the chance probability as a function of our FRB 1 sigma localization uncertainty for 2 kind of spatially coincident FRBs. And the localization uncertainties that I'm using in this work are the header localizations. And so as you can see, the chance probability is very high. And it's not until we have, baseband localizations for all our FRBs, or even better, outrigger localizations, that we could really ever claim that an FRB and a GRB are spatially significant. Okay, so what do we do when we don't detect anything? We go ahead and calculate upper limits. So we had 7 GRBs, which were within the field of view at CHIME FRB at the time of their high energy emission. And then we had another 32 GRBs, which were within the field of view either before or after, where before is 6 hours and 12 hours is after. It's slightly arbitrary, but you can go ahead and take a look at my paper for more details on that. So to go ahead and calculate an upper limit, we would ideally have an FRB to act as a flux calibrator that's both temporally and spatially nearby to our FRB. But because we only detect, 2 to 3 FRBs at CHIME FRB per day, which might seem like a lot to most people, we can't actually satisfy both criteria at once. So we use a spatially nearby FRB as our flux calibrator, and then we use our system sensitivity metrics to account for temporal differences. And then we use models of our beam to account for kind of minute differences between the location of our GRB and the location of our flux calibrator FRB. And so what I'm showing over here on this plot on the right is what these upper limits look like for one given GRB. This red star is the upper limit at the time of the high energy emission, and then these downward black arrows are either before or after. And so the limit at the time of the high energy emission for this GRB isn't too constraining, it's 1,000 Janskis. But 8 minutes after, it's down to about 100 Janskis, and I'll just note that the shape of this plot here is solely determined by our beam shape, and I think it gives a really good depiction of our sensitivity as a source transits over CHIME FRB. So we've got a lot of limits. I've got 39 GRBs, so what can we do with all of them? So what I go ahead and do is I split my GRBs into short GRBs and long GRBs, where here I'm kind of solely defining that based on the T90 of the burst, which I know is a bit incomplete. You also need to take into account spectral hardness information, but I'm not really doing that in this work here, just for simplicity. And then I take all the GRBs detected by a given telescope, so either Swift-BAT or Fermi-GBM. Those were the ones that had these 39 GRBs. And then I go ahead and take, for every kilosecond time bin since the high energy emission, I take my most constraining limit from that kind of sample of GRBs. So on the left, I'm showing that for our short GRB sample, where our kind of best limits that we can place are roughly around 5 Janskis at roughly 8 and 10 hours post high energy emission. And then on the right, it's for long gamma ray bursts, and that plot is just much more filled in just because we happen to have way more long gamma ray bursts above the horizon at CHIME FRB, just coincidentally. Okay, so I'm definitely an observationalist, not a theorist, but I tried to do a little bit of work to constrain some models using these limits. So we didn't have any short GRBs in the time frame right around the high energy emission above CHIME FRB, so within the field of view. So I don't focus on any pre-merger predictions and instead solely stick to post-merger predictions. So the first one that I focus on is this model by Totani 2013, where you've got this pulsar-like emission. I just want to note that in both of these models, we have to make a lot of assumptions, so there are a lot of caveats to what we end up constraining. So we end up assuming this millisecond magnetar is produced, and then what I show in the upper right-hand plot is the predicted radio flux from this model as a function of both the radio efficiency, so those are the different lines, and as a function of redshift, because none of our short GRBs had redshifts available. And so this red line is our best flux limit of 5 Janskis, and then the blue line is the median short GRB redshift. So if you assume that the short GRB for which we can apply this 5 Jansky limit roughly 8 hours after the merger is at a redshift less than 0.82, then we can constrain the radio efficiency in this model to be less than 4 times 10 to the minus 4. And I should note here that this assumes the radio emission can escape, and there are definitely papers out there that argue that it might not be able to.
2 minutes.
Great. Okay. So then in the bottom plot, it's kind of the same idea, except now we've got this neutron star collapsing to form a black hole, And in this model, we're now also highly dependent on spectral index because we're really unsure of what the spectral index of the emission would be. So it's the same idea in this plot, except now the kind of straight lines are for a spectral index of -3. The dotted is for -2, and the dotted dashed is for -4. And so if we again assume that this 5 Jansky limit applies for a short GRB less than 0.82, then we can constrain the radio efficiency in this model to be less than 9 times 10 to the -5. If we assume that it's a bit less steep, this spectral index, then we can constrain it to be less than 10 to the -10, so that's actually very constraining. And if we assume that it's very steep, then we can't do quite as well. We're left at 10 to the really not even less than 10 to the -1. So that's all that I've got. I'm hoping what I've conveyed to you is that we are doing these searches at CHIME FRB. So we are looking for coincident FRBs and GRBs, not just using the first CHIME FRB catalog, but really our entire data set, even though that's only what I presented on here today. We've got some interesting short GRB limits, and we've got a lot of long gamma ray burst limits. I'm not exactly sure how to use them, so if you have any theories or any ideas for how I could, please reach out. And I really want to acknowledge that this work would not have been possible without the entire CHIME FRB collaboration. It really is a team effort. And I recently submitted this to APJ if you want to take a look. Also, They just told me to stand closer to the microphone, so I have no idea if anyone heard me.
No, people could hear you online. It's okay. Any questions for Alice? Casey.
Great talk. Obviously, the nearby ones are extremely informative. I wonder if you have any predictions for what the sort of time scale is or the sample size you need for FRBs from CHIME before you have one within, a few hundred megaparsecs, say. And you'd have very strict limits on the flux ratio.
Well, that just depends, I guess, on the short GRBs and people getting out and localizing them. So I guess you take this one sample of 500, we didn't happen to have any short GRBs like above the horizon right at the time of the higher energy emission. I would assume that if I did it with like close to our full sample now, we definitely probably would. But what we can say about those efficiencies really just depends on getting the redshifts, and there's less short GRBs published and redshifts are even fewer. I hope that answers your question.
Yeah, thanks.
Okay, there's a question in the Slack channel from Kelly Gorgie. Can you expand on the choice of 7 days for your search? And also, nice talk.
Yeah. Can you go back to my slides? The classic question. Yeah, okay. So this is the probability of having at least one temporal and spatial coincidence as a function of the time difference between a given GRB and FRB. And as you can see, when you get up to about 7 days, that chance coincidence gets fairly high, so much greater than 1%. You could argue, okay, well, why didn't you just stick within a time frame of 1 day? Great question, fairly arbitrary. I was just interested in a week.
Okay. If there's no further questions, let's thank Alice again. Okay, and this next talk is by Stella Ocker, Scattering Horizons for Fast Radio Bursts.
Okay, hi everyone. I'm a last year PhD candidate at Cornell working with Jim Cordes and Shami Chatterjee. And today I'll be talking about scattering horizons, which is both a metaphorical and literal term. Let's see. So scattering refers to multipath propagation, which arises from turbulent, small sub-AU scale density fluctuations in ionized media. And we observe scattering in 3 main ways, shown on the right. We see that scattered rays arrive at later times, and so we see this characteristic scattering tail, known as pulse broadening. Scattered rays also interfere with each other when they arrive at the observer, and this gives rise to frequency-dependent intensity modulations or scintillation. And scattered rays also arrive from larger angles, which is observed as angular broadening. And so these are all diffractive scattering effects. There is, of course, a whole other regime of scattering called refraction, which I'm not going to be talking about today. And today I'll be really focusing on pulse broadening, which has major implications for burst detection because pulse broadening smears bursts out in time, reducing the burst signal to noise and hence detection sensitivity. And so thanks to CHIME, we can start to examine the distribution of scattering for the FRB population. And here on the right, you can see that distribution for catalog 1. And you can see that CHIME sensitivity drops off dramatically for scattering times greater than 10 milliseconds at 600 megahertz, which is indicated by that gray region. And because of the number of bursts that are found with scattering times above that threshold, we now know that there is a substantial population of bursts that are not detected by CHIME because they have very large scattering times. And so a major open question is, where is this unseen population of FRBs, and where do they acquire this very large scattering? We know that scattering probably doesn't occur in the IGM. So on the right, you can see scattering time versus extragalactic DM for catalog 1. And there's really no evidence for any correlation between scattering time and extragalactic DM, which is what you would expect if the IGM did contribute significantly. And we also see from localized FRBs that there's really no evidence for scattering in the IGM. And localized FRBs also indicate that scattering in halos is negligible, at least for those sources. So the motivation of my talk is to address two main questions. The first is, where does scattering arise along FRB lines of sight? This has implications for using scattering to probe particular ionized media of interest. And then the second question is, are there observable FRBs at redshifts greater than 1, which of course has major implications for proposed cosmological applications. And so the way that we address this question is by simulating the scattering distributions of an all-sky FRB population. In this case, I'm considering source redshifts between 0.5 and 5. And our key findings include that simulated scattering at redshifts less than 1 is dominated by host galaxies, but intervening galaxies start to dominate scattering once you get to redshifts greater than 1. And we also find that a significant fraction of high redshift FRBs have large scattering times, and by large I mean scattering times greater than 10 milliseconds at 1 gigahertz. So we simulate scattering using the ionized cloudlet model shown here. The pulse broadening time tau for a given line of sight component is related to the observing frequency nu. This geometric leverage factor G scat, which depends on the location of the scattering medium along the line of sight. F tilde, which is the fluctuation parameter. This quantifies the degree of turbulence in the ionized medium. The dispersion measure, DM, and lastly, the redshift of that scattering medium. And so we model the scattering contributions of different line of sight components, which are indicated in this diagram. We model the scattering contribution of the Milky Way using NE 2001 for the disk, and then we use a halo density profile from Prochaska and Zhang for the Milky Way halo, which is combined with empirical scattering limits for the halo based on localized FRBs with precise scattering budgets. So for other galaxies along the line of sight and also host galaxies, we develop independent, simple ISM and halo density models that account for a range of galaxy types, masses, and strengths of turbulence. And so we ignore scattering in the IGM because it appears to be negligible, and we also don't explicitly model scattering from local environments in this work. So here I'm showing you the scattering that is predicted from the Milky Way disk by NE 2001. For galactic sources shown on the left, the scattering time depends strongly on the distance to the source. And so these contours are showing that for lines of sight towards the inner galaxy and through the galactic center, scattering becomes prohibitively large. And this really refers to the scattering horizon, the region beyond which pulses become essentially undetectable in the time domain. On the right, you can see the NE 2001 prediction for extragalactic sources at a range of observing frequencies. And so this bright region in the galactic plane again shows you the scattering horizon from the Milky Way, and as you go down an observing frequency, that region becomes larger and larger. But of course, when you're looking at an all-sky population of FRBs, the Milky Way disk doesn't make a huge impact on the total scattering distribution that's observed for all lines of sight. It's really a strongly line-of-sight dependent effect. So here I'm showing you the DM and scattering time distributions that we simulate for local galaxies within 100 megaparsecs of the Milky Way. These galaxies are drawn from the gravitational wave galaxy catalog. And we model these galaxies based on their galaxy type, and this includes a galaxy type dependent component for their ISM and a more generic model for their halos, which only depends on the halo mass. And so you can see from the sky map on the right is that these nearby galaxies appear to really contribute negligible scattering to FRBs. These are simulated for FRB source redshifts greater than 0.1. But you'll also notice that scattering potentially is quite large near and through the ISM of the Magellanic Clouds, which are on the bottom right of the sky map. And so that's a particularly interesting region of the sky to probe further. So as we go to farther and farther distances, it becomes impractical to rely on a galaxy catalog to simulate scattering, so we start to do this in a statistical way. And here on the right, on the left, I'm showing the mean number of galaxy intersections as a function of source redshift. And we calculate this for intersections within twice the virial radius of a halo for a range of halo masses. And so halo intersections become exceedingly probable the farther back in redshift you go. And every time you intersect a galaxy, the scattering time will add linearly. And so FRBs accumulate scattering the more intersections they get. The dashed lines on this plot are showing the predicted mean number of intersections for galaxy disks. And you can see that galaxy disks are very rare to intersect, but when they are intersected, they can yield extremely large scattering to the point where if an FRB intersects a galaxy disk, it's probably not going to be observed. So we also simulate scattering from host galaxies. Here on the right, you can see the distribution of scattering time versus DM for host galaxies in the rest frame. We simulate 3 different galaxy types, dwarfs, spirals, and ellipticals, which we draw using the galaxy stellar mass function. And you can also see in black estimates for localized FRBs. And so for known localized FRBs, their scattering times really do seem to be dominated by their host galaxies. And what this means is that measured scattering times can inform FRB galaxy associations and potentially constrain the FRB location within the host. And it also means that scattering times attributed to host galaxies can be used as a basis for a combined DM scattering time redshift estimator, which is something that Jim Cordes has been working a lot on. Oh God, too much. Okay, so here I'm jumping ahead and showing the cumulative DM and scattering time distributions for an all-sky FRB population at 3 source redshifts, 0.5, 1, and 5. And so these distributions include the contributions of the Milky Way, galaxies within 100 megaparsecs, more distant galaxies, and also host galaxies. And the main trends are that scattering is dominated by host galaxies for redshifts less than 1, but then intervening galaxies start to dominate these distributions by redshift 5. And the really key implications that I want to point out is that based on these simulated distributions, 20% of FRBs from redshift 5 are predicted to have scattering times greater than 10 milliseconds at 1 gigahertz. And 40% of FRBs from redshifts greater than 0.5 are predicted to have scattering times greater than 1 millisecond below 800 megahertz. And so this is a potentially significant fraction of FRBs and arguably very conservative limits on the percentage of FRBs that are affected by scattering, because we haven't included features like local environments or potentially higher redshift enhanced CGM turbulence, which could dramatically increase the effect of scattering on the FRB population. And so there really is a potentially large fraction of high redshift FRBs that are unobserved due to scattering. So with that, I will take any questions.
Questions for Stella? There's a question on Slack here. Surya Bethapodi asks, would it be possible to estimate scattering times given a pointing?
Given a particular pointing.
He's in the room, you could just ask.
Oh,
Yeah.
oh,
I'm going to call him out.
okay, what to do?
Yeah, so would it be possible to estimate scattering times given a pointing based on your modeling?
Yeah, I mean, if you like have the galaxies in that pointing and they're, stellar masses, for example, yes,
Okay.
yeah.
Cool. There are other questions, but I'll let others ask.
Okay.
Okay.
Yeah, thanks for the talk. So even if at low redshifts you don't expect to see a correlation between scattering and DM, when you go further you should start to see that correlation, right?
Yeah, so it really depends on the evolution of turbulence in the IGM, which we don't fully understand. I mean, there are certainly theoretical predictions for what should happen. And it's possible that a correlation would emerge for higher redshift sources, but...
Yeah, I just mean like based on the fact that you would expect more intersections with foreground.
Yeah, so I think the correlation would be pretty marginal, to be honest. But yes, it is true that more distant would have higher scattering because of more intersections and also larger DM, but I don't think that the correlation would actually be very strong.
Okay, there's another question on Slack from Ryan Shannon. I might have missed it. Apologies if so. Was the CGM included for intervening galaxies?
Yes, yeah, the CGM was included, yeah.
Okay, and yeah, we're basically out of time, so let's thank Stella again.